On Saturday the 18th of July, that patch of the sun was completely empty. 3 days later, it measured 100,000 kilometres across, wide enough to swallow 7 Earths. 30 dark spots had assembled themselves where nothing at all had existed before. Forecasters gave it the highest magnetic complexity rating that their classification system contains. They doubled the odds of a major flare, and it was pointed directly at us. Then active region 4493 went quiet, and it did almost nothing. So here is the question I cannot answer, and the one this whole night circles. Is a sunspot that goes silent the most dangerous kind there is? Subscribe so you don't miss tomorrow's debrief, and tell me where you're watching from. Now let's get into it, starting with the 4 days that produced all of this. Part 1. The patch of sun that was empty on Saturday. On the 18th of July, 2026, that region of the sun was blank. Not quiet, and not decaying, but genuinely blank in every instrument pointed at it. Nothing appeared in the magnetograms, and nothing appeared in the white light imagery. No observatory tracking the disk had flagged that longitude as worth a number. Sometime in the 24 hours that followed, something underneath the surface pushed upward. Costantino Sigismondi works at Icaranet Pescara and at the Pontifical University in Rome. On the 21st of July, he filed a formal notice to the astronomer's telegram. His wording matters, so I want to give it to you almost exactly. The region emerged on the 20th of July, near the solar centre, already complex. He measured it at 120 millionths of the solar hemisphere. By the next day he recorded the area at 280 millionths. Let me translate those units, because they are doing an enormous amount of work. Millionths of the solar hemisphere is the standard measure of sunspot area. It sounds like a tiny fraction, and in one narrow sense it is, but it is a fraction of an object 1,390,000 kilometres across. 280 millionths means a magnetic structure larger than several Earths. By the time the Space Weather Prediction Centre published its summary, the numbers had moved. Region 4493 sat at North 5, West 5 in heliographic coordinates. That position places it almost exactly at the centre of the disk facing us. Its area was recorded at 300 millionths of the solar hemisphere. Its longitudinal extent was 10 degrees, and its spot count had reached 30. The magnetic classification field on that summary read Beta Gamma Delta. 30 individual spots, assembled in roughly 2 days, in a place that was empty. The Romanian solar imager Maximilian Vlad Teodorescu photographed the region as it grew. He described what he saw through his telescope as a gigantic ring of sunspot. He put it at 100,000 kilometres wide, spacious enough to swallow 7 Earths. Hold that image, because almost every summary of that week gets the next part wrong. 2 large regions sat relatively close together on the disk that weekend. They were catalogued as 4492 and 4493. Coverage at the time frequently treated the 2 of them as a single story. They were not the same story at all, and the difference is operational. The region numbered 4492 was a returning 1. The Solar Influences Data Analysis Centre in Brussels keeps its own numbering of sunspot groups. Their records identified 4492 as the return of an older group. The Americans had previously catalogued that same group as 4479. It had crossed the Earth-facing side of the Sun about a month earlier. It went around the back of the star, survived the trip, and came back. The region numbered 4493 had done none of that at all. Brussels instead assigned it a completely new group number of its own. It had no history and no previous rotation on any record anywhere. It was not a survivor coming around for a second pass at us. It emerged in place, near the centre of the disk, already aimed at this planet. Here is why that distinction matters to the people whose job this is. A returning region is a known quantity. Because they watched it for a full rotation. They know how it behaved, they know its decay rate, and they have a baseline. When it reappears over the eastern edge, they can make reasonable statements about it. A region that emerges in place near disk center offers absolutely none of that. Nobody has watched it do anything, because there was nothing to have watched. It arrives already loaded and already aimed at the planet underneath it. Forecasters are reading it cold, in real time, while it is still growing. There is one more thing about that position worth stating clearly. North 5, West 5 is not merely near the centre of the disk, it is the worst possible place for a complex region to sit. From there, anything the region throws outward travels roughly along our line, a few days earlier or later in its rotation, and the geometry changes. The same eruption would pass wide of us and become a curiosity. So the region did not just appear at maximum complexity, it appeared at maximum complexity in the one location that matters. Forecasters had a fully loaded structure pointed directly down the barrel, and they had no history on it whatsoever to work from. Stay with me, because the growth rate is what genuinely got attention that weekend. 120 millionths on the 20th, then 280 on the 21st, 18 spots on the first day, and 30 spots on the second one. That is not a region settling calmly into a stable magnetic configuration. That is a structure being driven hard from underneath, faster than it can organise. The disorganisation is the entire point, and the mechanism behind it is simple. When magnetic flux emerges slowly, the field lines have time to sort themselves out. Opposite polarities drift apart, and the structure relaxes into something stable and harmless. When flux emerges fast, those field lines get shoved into each other and stay shoved. Energy that would have leaked away gradually stays locked in place instead. Jan Alvestad maintains one of the longest-running independent solar activity records available. He noted that 4493 contained multiple magnetic delta configurations, not one. He located the smallest of them in the leading spot section of the group. He placed the most significant one in the intermediate section, between the two ends. The word that should stop you there is multiple, and I will come back to it. I want to leave you holding a single number before we go any further tonight. It will return 3 separate times, and it will mean something different each time. The number is 83%, and here is exactly what it counts. That is the share of every X-class solar flare across 28 years of records. All of them came from regions carrying the magnetic signature that 4493 built. It assembled that signature from nothing in roughly 48 hours while facing us. And then, having built it, the region did not fire at all. Whether that failure means what everybody assumed sits underneath everything tonight. But before I can reach it, you need to see what the region actually did. The hour-by-hour log tells a story every summary version left out. Part 2. 3 days of gunfire, and then nothing. Let me rebuild what happened between the 20th and the 23rd of July, not as a news event, but as a physical sequence with a clock attached. The region fired a C2.1 flare before it even had a number. That peaked at 7:39 in the morning Universal Time on the 20th. C-class is small, and it is genuinely unremarkable during any active period. Events that size happen dozens of times weekly, and get logged and forgotten. 7 hours later, the same patch of sun produced an M2.5. That flare peaked at 1436, 1 full order of magnitude higher. The measuring scale comes off X-ray sensors aboard weather satellites in geostationary orbit. That scale is logarithmic, so each letter up represents a factor of 10. Keep that in mind, because the jumps are far larger than they sound. An M flare is 10 times a C, and an X flare is 100. The M2.5 produced an R1 radio blackout over the Atlantic Ocean. R1 sits at the bottom of the blackout scale, and here is the meaning. High-frequency radio degraded across the sunlit face of the planet for tens of minutes. That band still carries transoceanic aviation, maritime traffic. and emergency services in remote regions. 4 hours later, an M1.1 peaked at 1920 Universal Time. That one produced an R1 radio blackout over Baja California in northern Mexico. 3 hours after that, an M3.4 peaked at 2225. That one produced an R1 radio blackout across the Hawaiian Islands. 3 M-class flares in under 8 hours from a region 2 days old. Each struck a different longitude because Earth kept rotating underneath the same fixed gun. The following day it fired again, an M1.7 at 1727. That produced an R1 radio blackout over the east coast of Mexico. Here is a small detail I find useful because it shows how this science works. The Brussels Centre logged that same flare as an M1.9 instead. The Americans and the Europeans watched one explosion on one star at 1 second. They came away from it holding 2 different numbers entirely. That is not a scandal, and it is not incompetence on anybody's part. It is cross-calibration between instruments with different processing chains and different baselines. The gap is about 2/10 of a class, which is genuinely small. You will see far larger disagreements later tonight over much bigger events. When they arrive, I want you already holding the idea that measurement carries uncertainty. On the morning of the 22nd, at 6:35, it fired its largest. An M3.6, producing an R1 radio blackout over India. That flare was the peak, and it was the top of the entire curve. Across that same 24-hour window, the region dominated the star completely. It accounted for 23 of the 24 flares recorded across the whole disk. Not 23 of its own flares, but 23 out of 24 total. Every other active region on the visible sun produced one flare between them. C. Alex Young is Associate Director for Science in the Heliophysics Science Division at NASA Goddard. He also writes the daily solar summary for EarthSky, and he called it a powerhouse. He noted that with maximum complexity, the region likely had more in store. The forecasters at the Space Weather Prediction Center clearly agreed with his reading. They raised the X-class flare probability from 5% up to 10%. They put M-class probability at 55% for the following 2 days. Then, with all of that loaded and aimed, the region simply stopped. On the 23rd of July, it still produced 10 of the day's 13 flares. It remained the dominant feature on the star by a wide margin. But the largest of those 10 was a C5.3 before dawn. C-class, which is to say back down into the ordinary background noise. No X-class flare occurred at all, not one, across the entire episode. The coronal mass ejection picture is equally undramatic, and I want to be direct. On the 20th, forecasters catalogued 4 separate ejections coming off the sun. None of those 4 were expected to reach Earth at any point. On the 21st, a filament erupted nearby and threw material outward before noon. That one was described as partially Earth-bound, but also as a faint event. By the 22nd, coronagraph imagery showed no Earth-directed ejections whatsoever. So let me state the situation plainly, because I will not oversell you anything. Active region 4493 did not hit us in any sense. It did not come anywhere close to hitting us at all. It produced 5 moderate flares, 5 brief radio blackouts, and 1 faint cloud. Then it quietly subsided back into the ordinary background of the star. And that is precisely where this stops being reassuring, for a reason in the same telegram. Sigismondi noted something about every dominant region of this particular year: 4479, 4473, 4419, and 4366. Each showed intense activity for only about 3 days before quieting down. 3 days of noise, then silence, repeating across the whole year. Against that pattern he set one exception. And the exception is why nothing here is comfortable. Pay close attention to this next comparison, because everything later rests on it. The superactive region of 2024 was first catalogued as 3664. It came back around as 3697 and then as 3723. It survived nearly 3 full rotations, 94 days, producing 969 flares. 4493 behaved like the ordinary ones, 3 days of noise then quiet. But 3664, the exception that lasted 94 days, did something specific. It produced the most powerful geomagnetic storm to strike this planet in 21 years. That storm cost American farmers $565 million. And I will explain how. Not one of them saw a flash of light in the sky. Not one of them lost electrical power for a single second. The difference between an ordinary region and a $500 million one is invisible early. That has always been the problem, and it starts with what these things physically are. Part 3. Why the darkest thing on the sun is not dark. The sun does not have a surface, and starting anywhere else makes this impossible. Almost every mental image people carry of this object is wrong in that specific way. What you see through a filtered telescope is called the photosphere. It is not a surface in any sense you would recognize from Earth. It is simply the depth at which the plasma becomes transparent enough to escape. Above that depth, photons fly free across the solar system. Below it, they are absorbed and re-emitted over and over again. A single unit of energy made in the core takes roughly 100,000 years to escape. The photosphere is not a boundary at all, but the altitude where fog clears. Underneath that layer, the outer third of the sun is boiling. Hot plasma rises, cools at the top, sinks again, and rises once more. Imaged at high resolution, it looks like a pot of boiling rice. Each of those convection cells is roughly the size of Texas. I want you to keep that boiling pot in mind, because it returns twice tonight. Now, that plasma is electrically conductive, and the whole star is rotating. It rotates at different speeds at different latitudes and different depths. The equator goes around in about 25 days, and the poles in 35. Conductive fluid moving through a magnetic field generates electrical currents inside itself. Those currents generate magnetic fields of their own, and the arrangement feeds back. That process is called the solar dynamo, and it winds the field progressively tighter. It does that across a cycle averaging roughly 11 years from end to end. That 11-year figure is an average rather than a rule. Individual cycles have run as short as 9 years and as long as 14. And the sun has stopped producing spots entirely for decades at a time. Between roughly 1645 and 1715, sunspots nearly vanished from records. That period is called the Maunder Minimum, and observers at the time noted it. Astronomers went years without recording a single spot on the disk. So the cycle is a tendency in the data, and not a clock. At the peak of each cycle, the sun's global magnetic field flips over. The north magnetic pole becomes the south, and the south becomes north. That reversal is not sudden, and it takes months to complete. During it, the field is at its most disorganized and tangled. A sunspot is what happens when part of that wound field breaks through. A bundle of intense magnetic field becomes buoyant and rises through the convection zone. When it reaches the photosphere, it punches through, and we see the result. Here is the part that actually matters, and it is not intuitive at all. Magnetic fields resist the motion of the plasma they are embedded within. Inside a large sunspot, the field can reach several thousand Gauss in strength. That is a few thousand times the strength of the field at Earth's surface. Where the field is that intense, the boiling underneath is suppressed entirely. The rising columns of hot plasma that carry heat upward get pinned in place. So the heat simply stops arriving at that patch of the surface. The photosphere around a sunspot runs at roughly 5,800 Kelvin. Inside the dark core of the spot, called the umbra, it falls further. Temperatures there drop to somewhere near 3,800 Kelvin instead. That is a difference of 2,000 Kelvin across a boundary you can see, and this is the detail that reframes the entire picture for me. A sunspot is not actually dark in any absolute sense. A sunspot at 3,800 Kelvin is ferociously bright. Cut one out and hang it alone in the night sky above you. Picture that for a second, because it inverts everything the images suggest. It would be one of the brightest objects you had ever seen. It would be painful to look at directly, without any filter at all. It looks black in the images only because it sits beside something hotter. The darkness you see is a contrast artifact, and nothing more than that. The spot is a hole in the heat flow, not a hole in the star. Every image you have ever seen of a sunspot is an optical illusion. Around the umbra there is usually a lighter filamentary ring called the penumbra. There the field lines are inclined rather than vertical, so convection is only partly suppressed. Look at high-resolution imagery of a penumbra and you can see individual filaments. Those filaments are the magnetic field lines, made visible by the plasma trapped along them. Hold that structure in your mind, because everything that follows depends on it. A simple sunspot group is bipolar, which is the ordinary and boring arrangement. There is a leading spot of one polarity and a trailing spot of the opposite. Field lines arch up out of one and back down into the other. It looks exactly like iron filings arranged around a bar magnet on paper. In the classification scheme developed at Mount Wilson Observatory, that arrangement is called beta. It is by far the most common configuration on any given day. Roughly 64% of all sunspot groups are ordinary beta groups. Beta regions are, statistically speaking, the dull majority of what appears. They flare occasionally, and they rarely do anything anyone outside the field hears about. A single isolated spot of one polarity is called alpha, and it is quiet as still. Then the classification system starts describing arrangements that are harder to draw. Gamma describes a bipolar group, where the polarities have become badly intermixed. You can no longer draw a clean line separating the positive region from the negative. The magnetic geography of the group has become genuinely complicated to map. And then, past gamma, the scheme runs out of gentle language entirely. What comes next is the configuration that 4493 assembled twice over. It is the arrangement responsible for almost every large explosion this star has ever produced. Part 4. The knot that fires 8 out of 10 of them. A delta configuration is defined in a single sentence that hides everything important. Two umbrae of opposite magnetic polarity, sharing one continuous penumbra between them. Read that slowly, because the physical meaning is not obvious from the words. Two magnetic poles of opposite sign, not separated by ordinary photosphere at all. Not sitting comfortably at either end of a relaxed magnetic arch. Instead, they are crushed together inside a single structure, within a few thousand kilometres. There is nothing between them, and nothing holding them apart except momentum. Think about holding two bar magnets, one in each of your hands. Turn them so the north pole of one faces the north of the other. Now push them slowly together and feel the resistance building in your forearms. That resistance climbs steeply, and it climbs faster the closer the two get. You can hold them nearly touching if you are willing to work at it, but the entire time you are doing that, you are storing energy in your arms. The arrangement stays stable for exactly as long as you keep holding it. A delta sunspot is that arrangement, at a scale that stops being imaginable. Each of those two magnets is larger than the planet you are standing on. What holds them together is the momentum of plasma flows in the convection zone below. The boiling pot underneath is what keeps your arms closed on the magnets. And the energy is not stored inside either spot, which surprises most people. The energy lives in the boundary between the two of them. That boundary has a formal name, the polarity inversion line. In a delta region, it is a place of extreme magnetic gradient and shear. Field lines pointing in nearly opposite directions run alongside each other for tens of thousands of kilometres. That is a loaded configuration, and the statistics on loaded configurations are unambiguous. Guo. Lin and Deng published their analysis in monthly notices of the Royal Astronomical Society. They worked through 28 years of continuous flare and sunspot records. Their finding is the 83% figure I asked you to hold earlier. 83.34% of X-class flares came from beta-gamma-delta groups. 62% of M-class flares came from the same category. 43% of the smaller C-class flares came from there too. Notice the gradient running through those three numbers, because it says something specific. The bigger the flare, the more overwhelmingly it comes from one place. Small flares happen more or less everywhere on the star, but large flares happen almost exclusively inside these tightly wound magnetic knots. Shai and Wang, working earlier, put the X-class figure even higher. More than 95% of X-class X-ray flares occur in delta regions, so the classification field reading beta-gamma-delta was not a routine catalogue entry. That was the specific signature behind almost every major solar explosion ever recorded. It appeared on a region that had emerged from nothing 8 hours earlier, and it sat at north 5, west 5, meaning the centre of the face pointed here. That is why the odds went up, and that is why people were watching. Now here is the other half of the statistics, and it carries equal weight. The story does not work honestly if I only give you the frightening half. Norton and colleagues examined solar cycle 24 in detail. They found that only about 8% of active regions are delta spots, and of those delta spots, only about 10% produce an X-class flare. That figure is 10%, and it is worth repeating slowly. Only one delta region in 10 ever produces an X-class flare. The correct reading of a delta region is not that it will explode. It is that this is one of the few structures physically capable of exploding, and if it does, there will be almost no warning worth the name. Which means active region 4493 did exactly what delta regions usually do. It sat there fully loaded, and then it quietly came apart without firing. Hold that 90%, because it becomes the most important number tonight. It will not mean what you currently think it means when it returns. There is a term for the energy sitting in that arrangement. Physicists call it free magnetic energy, and the name is precise. It is the energy above what the field would hold if relaxed. A relaxed field, with no shear and no twist, stores the minimum. Every degree of shear you add pushes the total above that floor. Free magnetic energy is the difference, and it is what a flare spends. You cannot measure that quantity directly from Earth with any instrument. It has to be inferred from surface magnetic field measurements and models. Those models extrapolate upward into a corona nobody can measure directly, which means the single number that matters most is always an estimate. Let me give you the analogy that solar physicists themselves reach for here. Imagine a balloon being inflated slowly, steadily, from a pump you cannot see. At the same time, someone is letting small amounts out through a pinhole. The air escaping through that pinhole is completely real and clearly measurable. You can hear it hissing, and you can feel it on your hand. If you measured only the escaping air, you would conclude it was deflating. But if more air goes in than comes out, the balloon keeps filling. But the pinhole is not functioning as a release valve at all. The pinhole is a distraction from what the pump is doing. The 5 M-class flares were the pinhole, and nothing more than that. 5 moderate events, 5 brief blackouts, and a great deal of activity in the logs. Meanwhile, the region continued emerging, continued growing, and doubled its total area. It added 12 more spots and assembled multiple delta configurations while flaring. The flaring was not the region releasing its stored energy at all. The flaring was the region announcing that it had energy to release. Then the emergence stopped, the structure relaxed, and the energy dissipated the boring way. It leaked out through gradual reconnection and decay instead of one catastrophic release. That happened this time, and it happens roughly 9 times in 10. Stay with me, because I now have to show you the other outcome. When one of these lets go properly, the sequence is stranger than you expect. It is also far faster, and it arrives in 3 completely separate waves. Part 5. The 8-minute warning that is not a warning. When a delta region finally lets go, the process is called magnetic reconnection. The mechanics are worth understanding precisely, because most descriptions skip the part that matters. Field lines pointing in opposite directions get pushed together at the polarity inversion line. Under ordinary conditions in a plasma this conductive, that should be impossible. The magnetic field is effectively frozen into the material carrying it, but in a thin enough layer, at a sharp enough gradient, something gives. The field lines break and cross-connect into an entirely new configuration. That new configuration sits at a lower energy state than the old one. The difference between those two states has to go somewhere immediately. It goes into radiation and into accelerating charged particles toward the speed of light. A large flare releases on the order of 10 to the 25th joules. The framing NASA itself uses is as much energy as 1 billion hydrogen bombs. The equivalent tonnage runs to roughly 1 billion megatons of high explosive. For the largest events on record, the estimate climbs several times higher still. Those numbers sit so far outside human scale that they stop meaning anything. So let me give you the version that genuinely matters instead. Not how much energy arrives, but how fast, and in how many waves. Because a solar storm is not one event at all. It is 3 separate events, arriving at 3 different times. Each of the 3 breaks a completely different category of thing. The first wave is electromagnetic radiation, meaning X-rays and extreme ultraviolet light. It is released at the moment of reconnection and travels at light speed, which means it arrives here 8 minutes and 20 seconds after leaving the sun. I want to sit on that number, because it is not a warning time. 8 minutes and 20 seconds is simply how long light takes to cross. The observation and the arrival are therefore the same single event. No instrument anywhere can tell you a flare happened before its effects reach you. The information and the effect travel together at identical speed, always. The first thing anyone learns about a flare is that it has landed. What that radiation does on arrival is ionize the upper atmosphere. Only on the daylit side, because only that side is exposed. That ionization increases the absorption of high-frequency radio dramatically, which is why all 5 flares came with a radio blackout attached, and why each blackout landed wherever Earth happened to be facing at that instant. The Atlantic, Baja California, Hawaii, eastern Mexico, and then India. Those 5 locations are not a pattern in the sun's behaviour at all. They are a record of where our planet had turned at 5 separate moments. The second wave is particles, mostly protons, accelerated to near light speed. They do not travel in a straight line, because they carry electrical charge. Instead, they spiral along the interplanetary magnetic field toward us. They arrive anywhere from tens of minutes to several hours later. This is the wave that matters for anything outside the atmosphere. High-energy protons pass through spacecraft shielding and through human tissue alike. They cause single-event upsets, where one particle flips 1 bit. Whatever function depended on that single bit is now quietly corrupted. They degrade solar panels permanently, shortening the working life of satellites. They deliver radiation dose to astronauts in orbit above the atmosphere. At sufficient intensity, they reach crews and passengers flying over the poles. Earth's magnetic field funnels particles downward there, rather than deflecting them away. During the July episode, the probability of that kind of storm was assessed low. It ran somewhere between 1 and 5%, and it never happened. The third wave is mass, and this is the one that matters most. A coronal mass ejection is not radiation, and it is not a particle stream. It is a physical cloud of magnetized plasma weighing billions of tons. It travels outward through the solar system as a coherent structure. It is slow by the standards of the first 2 waves. A typical ejection takes 1 to 3 days to cross the distance. The fastest ones on record have done it in under a day. This third wave is the one that reaches down and touches the ground, but whether it does anything at all depends on one single variable. That variable has nothing to do with how large the eruption was. In my experience, this is the part almost nobody has ever heard. The variable is called BIS, and it is deceptively simple. It is the north-south component of the magnetic field inside the cloud. Here is where I need your full attention, because this decides everything. Earth has its own magnetic field, and at the boundary it points north. If the arriving cloud carries a field also pointing north, they press together. The two fields largely refuse to connect with one another at all. The cloud slides around the magnetosphere and continues on into space. You can take a direct hit from an enormous fast ejection this way. If BIS points north, you can get almost nothing out of it. If the arriving cloud carries a southward field, everything changes immediately. The two fields are now pointing opposite ways where they meet, so they reconnect in exactly the way field lines reconnected in the sunspot. The magnetosphere opens like a door, and energy pours through it. So the severity of a geomagnetic storm is not mainly about eruption size. It is about the orientation of a field inside a cloud. That cloud is 150 million kilometres away when it starts. And here is the part that should genuinely bother you about all this. We cannot measure BIS until the cloud has almost arrived here. There are spacecraft parked at the first Lagrange point, upstream of Earth. That is roughly 1.5 million kilometres toward the Sun. They measure the solar wind as it flows past them. That is our warning system, and it does work as designed. But at typical ejection speeds, consider the gap it actually buys between a spacecraft there measuring the field and the plasma striking us. Somewhere between 15 and 60 minutes, depending entirely on speed. That is the real warning time, and I want to be precise. Not days and not hours, but 15 to 60 minutes. That is how long you have to know what is coming. To know whether a cloud travelling 2 days does nothing or everything. Everything before that moment is a forecast rather than a measurement, and there is a recent study on exactly how good those forecasts are. The finding is not comfortable for anyone who works in this field. Part 6. The forecast that cannot beat a coin flip. Enrico Camporeale holds positions at Queen Mary University of London and Colorado. Simon Berger works at the National Centre for Atmospheric Research. In 2025, the two of them published a verification study together. It appeared in the journal Space Weather, and what they did was overdue. They took the operational solar flare forecasts issued by the Space Weather Prediction Center. They gathered them across a 26-year period, from 1998 forward. Then, they scored every one of those forecasts against what actually happened. Their finding was that the forecasts do not outperform zero-cost baselines. Specifically, they do not beat persistence, and they do not beat climatology. Let me unpack what that phrase actually means, because it is technical. Persistence is the method of assuming tomorrow will look like today. Climatology is the method of assuming tomorrow will match the long-term average. Neither of them requires expertise, instruments, modelling, or a human forecaster. They are, in the most literal sense, what you get for free. So here is what that result actually says, stated plainly. 26 years of expert operational forecasting, from trained people with world-class observatories. It performed about as well as assuming tomorrow resembles today. The study also found the forecasts were poorly calibrated in a specific way. It reported excessive false alarms, particularly for X-class flares, and it reported the same problem in what the authors call all-clear scenarios, meaning the forecasts are weakest at the two things you most want. The first is telling you that a large event is coming, and telling you, reliably, that nothing is coming at all. I want to frame this carefully, because it would be easy to be unfair. This is not a failure of competence by the people doing the work. It is a hard limitation imposed by the underlying physics itself. Here is what a solar flare forecaster can genuinely do. They can look at a region and assess its magnetic classification. They can measure its area, its spot count, and its structural complexity. Then, they compare it against the historical flaring rate for that class. Follow this next distinction carefully, because it is the one everyone misses. A beta-gamma delta region of 300 millionths has an observable rate. That rate is roughly 10% across the region's lifetime. So the forecaster writes down 10%, and that is honest. That is genuinely useful information, and it is also not a prediction. It is an actuarial statement about a category of object. It is the same kind of claim as an insurance table. Insurers know the accident rate for a category of driver precisely, but that table tells them nothing whatsoever about next Tuesday afternoon. What forecasters cannot do is tell you when a specific region releases. They cannot tell you whether it will release at all, and they cannot tell you whether the resulting cloud arrives southward. Those three separate unknowns stack directly on top of one another. Each is close to a coin flip in its own right. The product of three coin flips is why the whole enterprise struggles. So the honest summary of last week is straightforward and slightly boring. A region appeared carrying the signature associated with the largest known events. The people whose job it is raised the numbers accordingly. The region did not fire, and nobody involved was wrong about anything. A 10% event failed to occur, which is what usually happens. There is one more limitation worth stating, and it concerns geometry. A flare is a point event on a rotating sphere. The ejection that follows it travels outward as a broad structure. Whether that structure intersects Earth depends on where the region sat. A region at disk center throws material more or less at us. A region near the edge throws it off to one side. 4493 sat almost exactly at disk center that week, which means, had it fired, the geometry was about as bad as possible. That is the single fact that made the 10% matter. A 10% chance of a large flare from the edge is academic. The same chance from dead center is an operational problem, and that geometry only holds while the region faces us. Within a week it rotates away, and the same flare misses entirely. So the window of concern for any given region is short. It is roughly the time it takes to cross the disk. Now I want to address the question that always arrives at this point. If I leave it sitting there, it blocks everything that follows. The question is whether any of this represents a larger pattern, whether the sun is behaving unusually, and whether something is being downplayed, whether the frequency of these events is climbing towards something worse. The honest answer has two halves, and coverage usually gives only one. The first half of it is genuinely straightforward to state. There is nothing anomalous about a region appearing, flaring, and decaying. That is the ordinary behaviour of an ordinary star mid-cycle. The Sun runs a magnetic cycle averaging roughly 11 years. Cycle 25 began in December 2019 at a sunspot number near 2. Activity climbed steadily through the early 2020s from there. At any moment during an active period, several numbered regions are visible. Several of those can flare, and one or two will be complex. 4493 was a large, fast-growing example of a normal category. Its emergence was not by itself a sign of anything, and Sigismondi's own observation from Rome supports exactly that reading. Every dominant region of this year showed 3 days of activity, then quiet. 4493 fits the pattern of the year it appeared in. It is not an outlier at all, but a member of a series. So no, the Sun is not doing something unprecedented right now. Anyone telling you a single M3.6 flare proves escalation is wrong. That is the first half of the answer, and it is genuinely reassuring. Here is the second half, and it is where the rest of tonight lives. The reason to pay attention has nothing to do with strange solar behaviour. The Sun is behaving exactly as anyone would expect it to. This is the turn in the story, so let it land properly. The reason is that we have entered a specific phase of the cycle. Historically and repeatedly, that phase is when the worst events happen, and separately and completely independently, the thing standing underneath has changed. It has changed enormously in the space of 30 years. The same storm now costs vastly more than it once did. Two independent timelines, both running right now, moving toward each other. One runs on the sun, on a clock that predates anyone watching. The other runs down here, on a clock we built ourselves. We built it out of transformers, satellites, and positioning signals. The convergence of those two is the actual story tonight. 4493 is only the alarm clock that happened to ring. But to understand what that convergence means, we have to go backward. 167 years to the only event of its kind observed, and to a misunderstanding about it that has persisted ever since. Part 7. The night the telegraph ran with its batteries off, on the morning of the 1st of September, 1859, Richard Carrington was working. He was an English astronomer in his private observatory at Redhill in Surrey. He was doing what he did most mornings without incident. He projected an image of the sun onto a screen and sketched the spots. He had been tracking one large and complex group for several days already. At around 11:18 in the morning, 2 points of white light appeared. Not bright regions within the group, but points, and intensely so. They were bright enough that his first assumption was equipment failure. He thought a hole had opened somewhere in his projection apparatus. He believed unfiltered sunlight was coming through onto the screen. He ran out to find somebody who could witness what he was seeing. He returned in under a minute, and the 2 points had already moved. By then, they were visibly fading against the projected disk. About 10 kilometres away, an amateur astronomer named Richard Hodgson saw it too. He recorded the same event independently, with no contact between them. What the two of them had watched was a white light flare. That means an event energetic enough to outshine the photosphere itself. In visible wavelengths, briefly, it beat the surface of the sun. In the century and a half since, very few have ever been documented. It remains among the rarest observations anybody in this field ever makes. 17.6 hours later, the coronal mass ejection arrived here. Now I want to walk through what followed carefully, because the misdirection lives here. The auroras that night were genuinely extraordinary by any standard. They were seen at latitudes down to roughly 18 degrees from the geomagnetic equator. That means Panama and Colombia and Hawaii and the length of Cuba. There are accounts, widely repeated across many sources, of gold miners in the Rockies. They reportedly rose and began cooking breakfast in the middle of the night. The light was bright enough that they believed dawn had already arrived. Newspapers in the American Northeast reported people reading print outdoors at midnight. Sit with that image, because the beautiful part is the misleading part. That is the part of the Carrington event that everybody knows. The sky lit up, and it was beautiful, and it was harmless. Here is the part that actually matters, and it is almost never told. At the time, the most advanced technological network on Earth was the telegraph, thousands of kilometres of wire strung on poles, grounded firmly at both ends. And on that night, the entire system went completely insane. Operators reported sparks jumping directly from their equipment onto their hands. Several of them received genuine electric shocks at their stations. Telegraph paper caught fire in multiple locations across 2 continents. Systems disconnected from their batteries entirely continued transmitting messages anyway. They ran on current the storm itself was inducing in the wires. There is a documented exchange between operators in Boston and Portland that night. They agreed to disconnect their batteries completely and work on what they called auroral current, and they continued sending messages that way for around 2 hours. Consider what that means physically for a moment, because it is remarkable. A magnetic disturbance in space, 100 kilometres up and higher. It induced sufficient voltage in wires lying on the ground below. Enough voltage to run a communication network with its power supply switched off. That is the mechanism, and it is the single most important thing tonight. When the magnetic field around the planet changes rapidly, something happens underground. It induces an electric field in the conducting rock beneath your feet. That geoelectric field drives current through anything long and conductive lying there. Telegraph wires in 1859, certainly, and far more today. Pipelines, railway signalling circuits, undersea cables, and high-voltage transmission lines. These are called geomagnetically induced currents, and they are the whole problem. Here is the twist that reframes this entire subject, and I want it clearly stated. The danger from a solar storm has never been the flash of light. It has never been the radiation reaching the upper atmosphere. It has never even been the aurora, which is only the visible symptom. The aurora is the fever, and it has never been the disease. The damage happens on the ground, slowly, through a current nobody can see. It happens in equipment nobody has ever thought about once. The process makes no sound, produces no light, and offers no dramatic moment. Nothing about the mechanism looks like a disaster while it is occurring. It looks like a piece of machinery running slightly warmer than usual. In 1859, the most vulnerable thing we had built was telegraphy. So the consequence was burned paper, shocked operators, and a strange night. The question that follows is what the equivalent network is now, and what precisely happens to that network when this repeats. Two independent assessments have tried to put a number on that question. The National Academy of Sciences published a report on severe space weather in 2008. It estimated the cost of a Carrington-class event striking the modern United States. Their figure ran between $1 and $2 trillion in the first year alone. In 2013, Lloyd's of London produced its own study of the same problem. They worked with atmospheric and environmental research on solar storm risk to the grid. Their range came out at $600 billion to $2.6 trillion. The Lloyd's report also made an estimate about people rather than money. Between 20 million and 40 million people in the United States would face outages. Those outages would last, in their own words, from several weeks to 2 years. Hold that phrase, because I will show you exactly where it comes from. The explanation is far more mundane than you are probably imagining right now. That range runs to 1 and 2 years, not days. It is emphatically not a matter of 1 or 2 weeks. And on the intensity of the storm that produces that, the literature disagrees openly. I would rather show you that disagreement than quietly pick a number. The standard measure of geomagnetic storm intensity is the Deist index in nanotesla. It runs negative, and it runs further negative as the storm strengthens. Cliver and Dietrich, and separately Cisco and colleagues, produced one estimate. They put Carrington at around -850 to -900. Suratani and colleagues, working from the same historical magnetometer records, disagreed. They arrived at somewhere between -1600 and -1760. That is nearly a factor of 2 disagreement among serious researchers. It concerns the largest space weather event in all of recorded history. And they are all working from the same underlying set of observations. I am not showing you that to undermine anybody's credibility here. I am showing it because it tells you the honest state of knowledge. We have exactly one direct observation of an event this size. It was made by a man with a hand sketch and a projection screen. Beyond that, we have scattered magnetometer traces from observatories never designed for it. From that thin record, we are trying to prepare for a repeat. 130 years after Carrington, the modern equivalent found out. It happened at 2:45 in the morning, in winter. Part 8. 90 seconds in the dark at -15. On the 13th of March, 1989, the grid serving Quebec collapsed. It happened at 2:44 in the morning, Eastern Standard Time. I want to give you the most important number about that event first. Everything else about that night follows directly from this one figure. The number is 90 seconds, and it is worth pausing on. From the first protective relay tripping to complete network collapse, under 90 seconds passed. 6 million people lost electrical power across the province that night. The outage lasted approximately 9 hours before restoration was complete. The outdoor temperature that night was around -15 degrees Celsius. Here is the sequence of that night as investigators reconstructed it afterward. A coronal mass ejection had left the Sun several days earlier. It arrived at Earth carrying a strongly southward magnetic field. The magnetosphere opened exactly the way I described to you earlier tonight. Currents in the ionosphere intensified enormously above the northern hemisphere. The magnetic field at ground level began changing very rapidly. Quebec sits close to the auroral zone, so the disturbance overhead was intense. But there is a second factor, and it is why Quebec specifically. The province sits on the Canadian Shield, which is ancient igneous rock. That rock has extremely high electrical resistivity throughout its structure. That detail is not incidental at all, and here is why it matters. When a geoelectric field is induced in the ground, current must flow somewhere. If the bedrock conducts electricity well, the current flows through the rock. It dissipates harmlessly through the earth, and nobody ever notices. If the bedrock is highly resistive, the current will not flow through it, so it seeks out the best available conductor in the entire area. Across northern Quebec, that conductor was the Hydro-Quebec transmission system, more than 1,000 kilometres of high-voltage line running roughly north to south. It carried power from the James Bay generating complex down to the cities, and it was grounded at every single substation along the route. The current came up out of the ground and through the transformer neutrals. It ran along the lines and then back down into the earth again. What that does to a transformer requires one piece of background to understand. A power transformer is built for alternating current, and only for that. It has a core, and the magnetic flux in that core swings back and forth. It swings symmetrically, 60 times every second, within a designed operating range. Geomagnetically induced current is not alternating in any useful sense. Relative to a 60 Hz system, it is effectively direct current. Superimpose direct current on the alternating flux inside a transformer core, the swing immediately stops being symmetrical in both of its directions. On one half of each cycle, the core is driven into saturation. Think of it as a swing pushed steadily off-center by a constant hand. It still swings, but it now slams into the frame on one side. That single image explains almost every failure I will describe tonight. A saturated core cannot contain the magnetic flux inside it anymore. That escaping flux passes through the surrounding structural components instead. It goes through tank walls, clamping structures, and the windings themselves. None of those parts were ever designed to carry magnetic flux. They heat up, and they do not heat up uniformly. They form localized hotspots inside a sealed steel container. At the same time, a saturated transformer draws enormous reactive power. It also injects harmonic distortion back into the system around it. Protective relays across the network are designed to detect exactly that signature. To a relay, it looks precisely like an electrical fault. So the transformers began drawing reactive power the system could not supply. The harmonic distortion began tripping protective equipment right across the network. Protection took equipment offline, which increased load on whatever remained. That drew more reactive power, which tripped more protection in turn. That entire cascade took 90 seconds, from the first trip to darkness. And here is the detail from that night I find most instructive of all. It happened over 1,000 kilometres from the blackout itself. Almost nobody outside the industry has ever heard about it. At the Salem Nuclear Generating Station in New Jersey, something quietly failed. A generator step-up transformer owned by Public Service Electric and Gas overheated. Its internal insulation degraded irreversibly during that same overnight storm. The unit was worth around $12 million to replace. The replacement power required while it was out cost roughly $400,000 more. The state of New Jersey did not lose power that night. There was no blackout anywhere in the state at all. Nothing visible happened in New Jersey during the entire event. A transformer simply ran hot for a few hours and was destroyed. It sat well south of the auroral zone, in a state that slept through it. That is the mechanism I need you to hold on to now. It is not the dramatic collapse, which is memorable and genuinely rare. It is the quiet degradation, which is invisible and far more common. A storm does not have to switch off your lights to take something from you. The same storm was felt far outside the electrical system as well. The Trans-Alaska Pipeline recorded induced currents running along its length. That pipeline is 800 kilometres of steel, insulated and grounded. It behaves electrically like an enormous conductor laid across the Arctic. Induced current in a pipeline accelerates corrosion at the joints. It also confounds the instruments used to monitor the pipe's condition. Compasses used for directional drilling gave false readings across northern latitudes. Satellites in low orbit tumbled as they hit thickened atmosphere. Some of them lost attitude control and took hours to recover. Tracking of objects in orbit degraded badly for several days afterward. The auroras that night were visible from Texas, Florida, and Cuba. The storm registered at KP9, the top of the planetary scale. The direct financial cost of the Quebec blackout was relatively modest. It came to around $13 million, of which $6.5 million was equipment. $13 million for the total collapse of a modern power grid. A grid serving 6 million people in the middle of winter. That figure sounds, on its face, almost reassuring to hear. Hold that number carefully, because it does not stay reassuring for long. In 2024, a much weaker storm cost 40 times more. It did that to a single industry, in a single country. And it did it without turning off anybody's lights at all. Before that, though, the sun produced something that broke the measuring equipment. Part 9. The flare that broke the instrument measuring it. In late October 2003, a region rotated onto the Earth facing side. It was catalogued as 10486, and it was enormous. Over about 2 weeks, it produced the most intense sequence ever monitored. On the 28th of October, it fired an X-17.2. The associated ejection left the sun at around 2,100 kilometers per second. It covered the distance to Earth in roughly 19 hours. That is close to the fastest transit anybody has ever recorded. It drove a G5 geomagnetic storm, the top of that scale. On the 29th, the same region fired an X-10. Its ejection travelled at around 1,950 kilometers per second. On the 2nd of November, it produced an X-8.3. And then, on the 4th of November, it did something unprecedented. The X-ray sensors aboard the geostationary weather satellites saturated completely. The flare exceeded the maximum value those instruments could physically record. The detectors flatlined at their own ceiling and stayed there. The figure entered into the record was X28. But that number is not the size of the flare at all. It is the size of the largest flare the instrument could register. Later reconstructions worked from ionospheric response data and other indirect measurements. They put the actual magnitude as high as X45. I find that detail clarifying in a way that raw statistics rarely are. We built an instrument to measure solar flares across their full range. We chose a ceiling that everyone involved considered generous at the time, and then the sun went straight through it without difficulty. The consequences that autumn were extensive, and mostly not blackouts. In Malmö, Sweden, a transformer-related failure cut power to about 50,000 customers. That is the one grid outage from the entire sequence. By the standard set in Quebec 14 years earlier, it was minor. In South Africa, 12 separate transformers were damaged during the storms. South Africa sits at a low geomagnetic latitude, far from the auroral zone. Conventionally, it is considered a low-risk region for this entirely. Track the losses as I list them, because they span the whole system. Japan's Adios 2 satellite, known as Midori 2, was lost outright. It carried the Seawinds instrument, a NASA scatterometer worth around $150 million. Roughly 59% of all spacecraft operating then experienced anomalies. Airlines rerouted polar flights away from the high-latitude corridors. Those routes lose high-frequency communication and take elevated radiation dose. Astronauts aboard the International Space Station moved into the most shielded sections. They stayed there and waited for the proton flux to fall. And a radiation instrument aboard Mars Odyssey was knocked out permanently. That spacecraft was in orbit around an entirely different planet at the time. That autumn also produced one of the strongest radiation storms on record. Protons accelerated by those flares flooded the near-Earth environment for days. Radiation storms are measured on their own scale, running from S1 to S5. That particular storm reached the upper end of that scale. For anyone in orbit, that is the genuinely dangerous part of a storm. Not the geomagnetic disturbance, which is a ground-level problem. The protons are what pass through hulls and through tissue. Crews on high-latitude flights accumulated measurable dose during those weeks. Airlines that continued flying polar routes were tracking it carefully. Several carriers simply stopped flying those routes until the flux dropped. The scientific instruments suffered as badly as the operational ones. Detectors designed to count particles were overwhelmed by the count rate. Some instruments were switched off deliberately to protect them from damage. Others recorded data that had to be discarded entirely afterward. There is a strange irony buried inside that particular outcome. The largest event of the satellite era partly erased its own measurement of minus 383 nanotesla. The planetary index reached KP9, the top of the scale again. The satellite positioning effects that autumn deserve their own mention here. The augmentation system used by American aviation was taken out of service. It was unavailable for roughly 30 hours during the storm sequence. That system exists specifically to sharpen satellite positioning for aircraft. Losing it does not ground anything, because older procedures remain available, but it removes a layer of precision that approaches depend upon. Power grid operators across Northern Europe and North America reported voltage swings. Several took precautionary action, reducing loading on their transmission systems. Those actions are invisible afterward, because nothing broke as a result. That invisibility is a recurring theme, and it matters later tonight. Now hold that against the Carrington figures from a moment ago. Even the most conservative estimate for 1859 was minus 850. That is more than twice as intense as the Halloween storms. The higher estimate for Carrington is over 4 times as intense, so consider what the 2003 sequence actually accomplished. It produced the largest flare ever recorded by any instrument. It saturated the monitoring equipment built specifically to measure it. It killed a satellite and damaged transformers on 2 separate continents. It disabled hardware in orbit around Mars, 80 million kilometres away. And it was somewhere between a quarter and half as severe as Carrington. The event we have exactly one hand-drawn sketch of. That is the calibration I want you carrying into what comes next. Because 9 years later, something at Carrington's level came back around. The only reason it is not the defining catastrophe of this century is timing. That timing was measured, quite literally, in a matter of days. Part 10. The one that crossed our orbit a week late. On the 23rd of July, 2012, an extremely fast ejection erupted. It came off the Sun and crossed the orbit of Earth directly. Earth simply was not standing at that point when it arrived. Our planet had passed through that exact point, roughly a week earlier. The eruption swept through the space we had recently occupied. Then, it continued outward into the rest of the solar system. Out there it struck the Stereo A spacecraft, which measured it in detail. Measuring events like that is precisely what Stereo A was built for. The measurements came back at around 2,500 kilometers per second. There were actually 2 coronal mass ejections involved, not one. They were released roughly 10 to 15 minutes apart from each other, and they were preceded by an earlier eruption from the same region. That first eruption had already swept the intervening space clear. It cleared out the slower solar winds sitting in the way. so the two main clouds travelled through a corridor prepared for them. Consequently, they lost far less speed than they otherwise would have. That detail matters more than it might appear at first. It is the same configuration that made Carrington so unusually fast. A preceding eruption clears the path through the inner solar system. The main event then arrives at close to its full launch speed. It is not a coincidence that the two most extreme events share it. Daniel Baker works at the Laboratory for Atmospheric and Space Physics in Colorado. He led the analysis of the 2012 event afterward. He and his colleagues published it in the journal Space Weather. It appeared in December 2013 under a deliberately flat title. They called it a major solar eruptive event in July 2012. What he said afterward is worth hearing in full, so listen closely. Baker's public statements about it are the most direct I have encountered. From a working scientist discussing a hypothetical disaster, they are unusually blunt. If it had hit, we would still be picking up the pieces. And then he addressed how it compared to 1859 directly. In my view, the July 2012 storm was at least as strong as the Carrington event in all respects. The only difference, he said, is that this one happened to miss. NASA modelled what the impact would actually have looked like here. The result came out at a DEIST of approximately minus 1,200 nanotesla. That figure is comparable to Carrington on the more conservative estimate. It is roughly twice as severe as the storm that took down Quebec. Now here is what I find genuinely unsettling about the whole episode. At the time it happened, in July 2012, essentially nobody noticed. There was no warning issued, because there was nothing to warn anyone about. There was no news coverage anywhere, because nothing had happened. The event only entered public awareness a full 2 years afterward. That happened in 2014, when Baker's team published their analysis. Only then did the world learn what had crossed our orbital path. A Carrington-class event had passed through 18 months earlier, and our survival that month had been a pure scheduling coincidence. Which brings me to the most quoted figure in this entire field. Pete Riley works at Predictive Science Incorporated, based in California. He published a paper in Space Weather in 2012. He worked from the statistical distribution of historical solar events. His goal was estimating the probability of another Carrington-class strike. The figure he arrived at was 12% per decade. His own public reaction to that number is worth repeating exactly. It is unusually honest for a scientist discussing his own result. Initially, he said, he was quite surprised the odds were so high. But the statistics do appear to be correct, he continued afterward. He called it, in his own words, a sobering figure. Riley and Jeffrey Love revisited that calculation in 2017 together. They treated the underlying distribution more carefully the second time. Fitting a power law gave 10.3% per decade. Fitting a log-normal distribution instead gave 3% per decade. So the range in the current literature runs from 3 to 12%. That is the probability across any given 10-year window. Take the low end of that range, the most conservative figure published. 3% per decade from the most cautious treatment available. Across a human lifetime, that is not a small number at all. And the 2012 event proves the rate is not theoretical. One of them physically crossed our orbit within living memory. We know its speed, because a spacecraft flew through it. We know what it would have done, because NASA modelled it. And the entire difference between anecdote and catastrophe was orbital position. There is one more consequence of a Carrington-class event worth naming. It concerns the cables that carry the internet between continents. Undersea fibre optic cable does not conduct electricity along the fibre itself, but the cable contains a copper conductor running its entire length. That conductor powers repeaters spaced along the seabed every few dozen kilometres. Those repeaters amplify the optical signal so it survives the crossing. A long-grounded copper conductor lying across an ocean floor is exposed. Induced currents can push the power feed equipment outside its operating range. If repeaters lose power, the cable stops carrying traffic entirely. This is not hypothetical, because smaller versions have been documented. Cable faults have been correlated with geomagnetic activity in the past. I am not predicting the internet fails during the next storm. I am pointing out that the same mechanism from 1859 applies. It applies to a network that did not exist 25 years ago, and almost nobody outside the cable industry has ever considered it. Stay with me, because I have now given you the sun's half. And the sun's half is genuinely the less interesting one. Everything so far has been about what the star does. Carrington, Quebec, the Halloween storms and the 2012 near miss. That behaviour has been roughly constant for as long as the star existed. The rate of these events was the same in the year 800. What has changed almost beyond recognition is what stands underneath, and it changed inside the span of one human lifetime. Part 11. The $500 million that nobody noticed losing. By August of 2024, active region 3664 had grown enormous. It measured somewhere between 3,300 and 4,400 millionths. Set that against 4493, which topped out at 300. Region 3664 was more than 10 times larger than last week's. Comparisons at the time put it near the size of Carrington's group. Its width was described as roughly 104 Earths across. It was classified Beta Gamma Delta, exactly like the region from last week. It produced a series of major flares including an X5.8. That one fired on the 11th of May, 2024. And unlike the 3-day regions of this year, it refused to decay. It went around the far side and came back as 3697. It went around again and returned once more as 3723. 94 days in total and 969 separate flares. The storm it produced in May is now generally called the Gannon storm. It reached G5, the top of the geomagnetic scale. That was the first G5 in 21 years since the Halloween sequence. Auroras appeared at latitudes that had not seen them in living memory. Now here is why I have built toward that storm rather than Carrington. The Gannon storm caused no major blackout anywhere on the planet. No grid collapsed, and there was no repeat of the Quebec moment. Transpower in New Zealand declared a grid emergency and took precautionary measures. Beyond that single action, the world's electrical systems held perfectly well. By the standard everybody uses to judge these events, it was nothing. The lights stayed on, so most people recorded it as a light show. It cost farmers across the American Midwest an estimated $565 million. That figure comes from Terry Griffin, an agricultural economist at Kansas State University. His estimate covers Midwestern crop producers during that specific week. It works out to somewhere around $17,000 per affected farm. Nobody lost power, and no transformer failed anywhere in that story. The mechanism was entirely different, and it did not exist in 1989. Modern precision agriculture depends completely on satellite positioning to function. Not the accuracy in your phone, which is measured in meters. This is real-time kinematic positioning, which is a different thing entirely. It corrects the satellite signal against a fixed ground reference station nearby. That correction achieves accuracy measured in centimeters rather than meters. That is what lets a tractor drive itself down a row precisely. Follow the chain from here, because it ends somewhere unexpected. It plants seed at exact spacing across an entire field. Then it returns weeks later to treat those same plants individually. When a geomagnetic storm disturbs the ionosphere, those signals scatter unpredictably. The delay through the disturbed layer becomes impossible to model accurately. The effect has a name, and the name is scintillation. The ground correction breaks down, and centimeter accuracy becomes unusable. The Gannon storm arrived during the second week of May. In the American Midwest, the second week of May is planting. receivers across the region lost their accuracy during the storm. Farmers faced a choice between planting badly and not planting at all. Planting badly compromises the yield across an entire growing season. So many of them simply stopped and waited for it to pass. $565 million from a few days of degraded signal. One industry, in one country, from a storm that turned off nothing. Compare that against the $13 million cost of the Quebec collapse. That was the total failure of a grid serving 6 million people. That single comparison is the shape of the entire change here. The grid remains the largest single risk, and I am not minimising it. But the modern economy has grown enormous new dependencies on space. Almost none of those dependencies are visible until the moment they fail. The same storm triggered compasses in seabed observatories deep below the Pacific. Researchers at the University of Victoria documented that effect afterward. Those instruments sat 2.7 kilometres below the ocean surface. That much water is an excellent radiation shield and a poor magnetic one. There is effectively nowhere on this planet a large storm does not reach. And then there is the orbital environment, which changed faster than anything else. On the 3rd of February, 2022, SpaceX launched 49 Starlink satellites. They went into a low insertion orbit, which is entirely standard practice. Satellites are placed low and then raised gradually over following weeks. That way, any unit failing its checks deorbits naturally rather than becoming debris. Then, a geomagnetic storm arrived, and it was not a large one. It was rated minor to moderate on every scale used. What that storm did was deposit energy into the upper atmosphere. That energy heated the atmosphere, which caused it to expand outward. Atmospheric density between 200 and 400 kilometres rose sharply. It increased by somewhere between 50 and 125%. Drag on anything flying through that region increased by around half. The Starlink team put the satellites into a knife-edge orientation immediately. That minimises cross-section, and it was exactly the correct response. It was enough to save 11 of the 49. 38 satellites could not overcome the drag at that altitude. They re-entered and burned up in the atmosphere around the 7th of February. 38 spacecraft lost in 4 days from an unremarkable storm. It would not have registered as an event on any historical scale. The episode has since been analysed in multiple papers in Space Weather. Now consider the scale of what is up there today. As of early 2026 there are over 14,500 active satellites. Starlink alone accounts for roughly 10,759 working spacecraft. That comes from orbital tracking maintained by the astronomer Jonathan McDowell. His running figures were last updated in July of this year. That single constellation is between 65 and 68% of everything operational. Weigh the next few numbers carefully, because the scale has changed recently. In January of this year, the Federal Communications Commission authorised further expansion. They cleared 15,000 second-generation Starlink satellites for launch, and in 2026, SpaceX began lowering roughly 4,400 satellites. They are moving from around 550 kilometres down to 480. Michael Nichols, the company's vice president for Starlink engineering, announced the decision. The stated reasoning was space safety, and it is entirely sound. Lower orbits mean faster natural deorbit for any satellite that dies. That directly reduces the long-term debris hazard for everybody. Lower orbits also mean substantially more atmospheric drag during a geomagnetic storm. I am not suggesting that trade-off was made carelessly by anyone. It is a reasonable engineering decision with genuine safety benefits attached. But it does mean the largest constellation ever built is moving downward. It is moving deeper into the layer that expands when the sun acts. Below that orbital layer, the dependencies stack up in ways nobody considers. Aviation reroutes polar flights during proton events, as I mentioned earlier. Those routes lose high-frequency contact and take elevated radiation dose. Financial systems depend on satellite timing signals for transaction timestamping. You cannot settle a trade without knowing precisely when it occurred. Maritime navigation, surveying, construction and mining run on the same signals. Those are the signals that failed Midwestern farmers in May 2024. Undersea communication cables carry almost all intercontinental data traffic today. They contain powered repeaters spaced at intervals along their length, and they are long, grounded conductors lying on the seabed. Pipelines are long grounded conductors, and so are railway signalling circuits. Every one of those is a telegraph wire on a pole in 1859. There are simply vastly more of them now than there were, and we have arranged society so each failure cascades into the others. Which brings me to the single component that decides everything. It determines whether a bad week becomes a bad decade. Part 12. The machine that takes 3 years to replace. I want to talk about extra high voltage transformers now. I am aware this is the least dramatic subject in the entire briefing. Stay with me anyway, because it is why Lloyds wrote 1 to 2 years. A large power transformer steps voltage up for long-distance transmission. Then, another steps it back down again for local distribution. Without them, electricity generated at a power station cannot reach a city. It is not a component of the grid so much as the grid. Everything else in the system is essentially wire between transformers. These machines are enormous physical objects by any reasonable measure. A large one weighs several hundred tons in operating condition. They are built to order, matched to the electrical characteristics of one location. There is no standard model anyone can pull off a shelf. Now here are the numbers, and they come from an official source. The United States Department of Energy published a resilience report to Congress. That particular report appeared in July of 2024. Lead times for extra high voltage transformers run up to and exceeding 36 months. Gap analyses cited in the same body of work go further still. They note that lead times can extend to 5 years in some cases. That is 60 months of waiting for a single replacement machine. A typical 100 megavolt ampere transformer takes 2.5 to 3 years. Cost runs between $2.5 and $10 million per unit. And a market survey by Wood Mackenzie examined the supply chain last year. It found roughly 80% of large power transformers used in America are imported. Those units come primarily from Mexico and from South Korea. Standard power transformers were averaging about 128 weeks for delivery. Generator step-up units were averaging around 144 weeks. 144 weeks is 2 years and 9 months of waiting. And a generator step-up unit is exactly what died at Salem. It is worth saying what these machines look like in person. A large unit stands several stories tall on its concrete pad. It is filled with thousands of litres of insulating oil. Radiators run along the sides to carry heat away continuously. A bank of them at a substation covers the area of a football pitch. They are also, in normal operation, almost entirely maintenance-free. A well-built transformer can run for 40 years without incident. That reliability is exactly what makes the supply chain thin. Nobody keeps a deep inventory of something that rarely fails. The economics of holding spare units are genuinely difficult to justify, which is fine, right up until a correlated failure hits many at once. Ordinary failures are independent, and independent failures are easy to plan for. A geomagnetic storm produces the opposite kind of failure entirely. It stresses every transformer across a region at the same moment. Now hold those delivery numbers against the physical mechanism from earlier. Induced current drives a transformer core into half-cycle saturation. Flux escapes the core and forms hot spots in structural components. The internal insulation degrades under that heat over a few hours. A transformer damaged that way frequently does not fail during the storm. Instead, it fails weeks or months afterward, apparently at random. Fix that delay in your mind, because it hides the damage completely, or it survives with a shortened life and fails during the next demand peak. The damage is cumulative, and it is largely invisible from outside the tank. So consider what the Lloyd scenario is actually describing here. It is not a storm that destroys a power station dramatically. It is a storm that quietly damages transformers across an entire region. Most of those units do not announce themselves at the time. The replacements are individually built to order for specific sites. They are largely manufactured overseas by a handful of suppliers, and they are delivered on a schedule measured in years. There is a further wrinkle in that supply chain worth understanding. These transformers are not simply large versions of a common product. Each is engineered for a specific voltage, a specific load, a specific site. The core steel involved is a specialized grade with limited global production. The manufacturing process requires enormous presses and clean assembly halls. Very few facilities anywhere in the world can build the largest units. So the constraint is not really money, and it is not will. The constraint is physical capacity that cannot be expanded quickly. If a dozen units are needed at once, the queue does not move. Everybody waits in the same line at the same speed. Together, the industry is fully aware of this problem and has responded. The Spare Transformer Equipment Program exists to pool inventory between utilities. So do Spare Connect and the North American Transmission Forum's Restoration Program. A damaged unit in one place can be covered from another. The Department of Energy's own assessment of those programs is measured. Its quadrennial energy review concluded they may not be adequate. I want to avoid overstating this, because a real counter-argument exists. Modern grids are far better instrumented than Hydro-Quebec was in 1989. Operators now have specific geomagnetic disturbance procedures written down and rehearsed. They can reduce loading and bring additional reactive power support online. They can take individual transformers out of service ahead of a storm. The North American Electric Reliability Corporation maintains standards addressing exactly this. That is genuine progress, and the recent evidence supports it. The May 2024 storm was a real G5 event. The grid held everywhere it mattered, and that is not luck. But notice precisely what all of that mitigation depends upon. It depends on the warning arriving with enough time to act. It depends on operators believing the warning enough to accept the cost, and that cost is real, because reducing transmission loading has consequences. And we established earlier what the warning actually consists of. The field orientation inside the cloud determines everything about the outcome. It cannot be measured until the cloud reaches the spacecraft upstream. That leaves operators somewhere between 15 and 60 minutes to act. 15 to 60 minutes to decide whether to degrade a continent's power supply. On the possibility that this particular hour is the bad one, now imagine making that decision for the fourth time in 2 years. Having been wrong, in the only sense that gets measured, 3 times already. That is the actual failure mode hiding inside all of this. It is not that nobody sees these things coming at all. People see something coming regularly, and it usually turns out to be nothing. The cost of responding is immediate and certain and appears on a balance sheet. The benefit is probabilistic and invisible, and appears nowhere at all, which is precisely the position 4493 created last week, and I want to show you what happens when that decision goes wrong. Part 13. 72 hours, hour by hour. I want to walk through a sequence now, and I want to bound it carefully. Everything in the next few minutes uses only documented mechanisms. I am not inventing a single new failure mode anywhere. Each element has already physically happened somewhere I have described, in Quebec in 1989, and in Malmo in South Africa in 2003, in low Earth orbit in 2022, and across the Midwest in 2024. The only speculative step is putting them all on one clock. At hour 0, a large delta region on the Earth facing disk fires. It releases an X-class flare directly along the line toward us. The X-rays arrive 8 minutes and 20 seconds later. The first anyone knows is that the effects are already present. High-frequency radio degrades or fails across the entire daylit hemisphere. Aircraft en routes without satellite coverage lose their primary contact method. They fall back to procedural separation, which is slower and more conservative. Emergency services relying on high frequency in remote regions lose it entirely. This lasts somewhere between tens of minutes and a few hours. Then it clears on its own, with no intervention required. At this point, nothing has happened that the general public would notice. At hour 1, if the flare accelerated protons efficiently, they begin arriving. Satellite operators start seeing single-event upsets in onboard electronics. Individual particles flip individual bits inside onboard processors and memory chips. Most of those errors are caught and corrected automatically by design, but some of them are never caught by anything at all. Spacecraft in the harshest radiation environments begin entering safe mode. That is the correct automatic response for any satellite to make. It also means they have stopped doing their actual jobs. Airlines begin rerouting polar flights southward around the exposed corridors. That adds fuel burn and flight hours to every affected route. Those hours cascade into crew duty limits and missed connections downstream. Astronauts move into the most heavily shielded part of the station. Between hour 2 and hour 6, coronagraph imagery confirms an ejection launched. It also confirms the thing is heading in our general direction. Now the forecasting begins, and now the fundamental limitation applies. Models can estimate an arrival time within a window of several hours. Notice what is missing from that forecast, because it is the whole problem. They cannot tell anybody the one thing that decides the outcome. They cannot measure the magnetic field orientation inside that cloud. So the message going out to grid operators is a probability. It carries an arrival window attached, and nothing more definite than that. From hour 6 through hour 40, the waiting period runs. That waiting period is what decides the outcome of everything else. Somebody in an operations center has to choose whether to act. Acting means reducing loading on transmission systems across a region. It means bringing additional reactive power support online across the network. It means taking specific name transformers out of service preemptively. And in some cases it means shedding customer load deliberately. All of that carries an immediate, certain, and measurable financial cost. All of it has to be justified to somebody afterward. Not acting costs absolutely nothing at all, most of the time. Because most of the time the cloud arrives with a northward field. At roughly hour 40, the cloud reaches the spacecraft parked upstream. That vantage point sits 1.5 million kilometres toward the Sun. For the first time, the field orientation is directly measured rather than guessed. The clock is now 15 to 60 minutes, and not 1 second more. If the field points north, the story ends quietly right there. There is a minor disturbance and some aurora at high latitudes. By the following week, the dominant impression is that nothing happened. A great deal of noise was made about nothing at all. If the field points strongly south and stays that way, everything changes. The magnetosphere opens and ionospheric currents intensify enormously in the sky overhead. Ground-level magnetic readings begin changing rapidly across whole continents. Induced currents start flowing through every long conductor in the region. Within the first few minutes, satellite positioning accuracy degrades badly. This is the Gannon mechanism, and it is the fastest visible effect. Precision agriculture stops working, and commercial surveying stops along with it. Anything depending on centimetre accuracy simply ceases to function properly. Aviation loses its most precise navigation aids and falls back. In the same window, transformers begin experiencing half-cycle saturation. That happens first in high-latitude regions over resistive bedrock. Reactive power demand then climbs steeply across the whole affected network. Harmonic distortion then propagates outward through the entire transmission system. Protective relays begin interpreting all of that as electrical faults. From a relay's point of view, it is genuinely indistinguishable. This is the Quebec sequence, exactly as it ran in 1989. There it took 90 seconds from the first relay to total darkness. Whether that repeats depends entirely on the decision made hours earlier. It depends on how much protective action was taken during the wait. And it depends on how heavily the system was loaded at that moment. A grid running near capacity on a summer afternoon has almost no margin. The same grid running light at 3 in the morning has plenty. Meanwhile, in orbit, the upper atmosphere is heating and expanding outward. 2 systems are now failing at once, and they do not know it. Drag increases on everything below roughly 600 kilometres altitude. Operators of large constellations are now managing thousands of spacecraft simultaneously. They are doing it through elevated drag and degraded tracking data. That tracking degradation quickly becomes its own separate problem entirely. Collision avoidance depends completely on knowing where every object currently is. From hour 40 through hour 72, restoration begins if a grid collapsed. And restoration is not a matter of switching things back on. It is a slow controlled procedure known as a black start. Generation and load are brought back in carefully balanced increments. Under genuinely good conditions, that process still takes hours to days. But the durable damage is not the outage at all. It is the transformers that saturated, ran hot, and quietly degraded. Those damaged units go back into service looking perfectly fine. Some of them fail weeks later, and some fail months later. They fail during the next demand peak, apparently at random. They get recorded as ordinary equipment failures in the maintenance logs, and each one takes 2.5 to 3 years to replace. Each costs between $2.5 and $10 million. Each comes from a supply chain that is 80% overseas, and that chain is already running 144 weeks behind on ordinary orders. That is the entire sequence, and every element of it has happened. The only thing I did was place them on a single clock. Now notice where the actual decision point sits in that timeline. It is not during the storm, when everything is obvious. By the time the field orientation is known, the outcome is fixed. The decision point is hour 40 and earlier during the waiting, when there is no information and somebody has to act on a probability. Which is exactly the position 4493 created last week. And it is exactly the position in which nothing whatsoever happened. Part 14. Hurricane season, and the phase we just entered. The current cycle, solar cycle 25, began in December 2019. It started at a smoothed sunspot number of 1.8, close to blank. A prediction panel convened by NOAA and NASA forecast what would follow. They expected the cycle to peak somewhere between 105 and 125. They expected that peak between November 2024 and March 2026. The actual smoothed sunspot number peaked at 160.8. That happened in October of 2024, earlier than the middle prediction. The unsmoothed monthly peak reached 216 in August 2024. So the cycle ran substantially hotter than forecast, and it peaked early, which means that as of now we sit roughly 21 months past maximum. All of 2025 and all of 2026 have been decline, and this is where the two timelines finally meet each other. So I want to lay out the second one very carefully. There is a documented pattern in the record that runs against intuition. The most violent geomagnetic storms do not cluster at the sunspot peak. They cluster in the declining phase of the cycle instead. Typically that means 1 to 3 years after the maximum passes. A team led by Ecker quantified that pattern directly in the literature. They found the rate of intense storms during the maximum and declining phases. It runs at roughly 3 times and 2 times the rising phase rate, and the individual historical cases line up with that, finding neatly. The Halloween storms occurred 2 to 3 years after the cycle 23 maximum. That particular maximum had arrived around the year 2001. The Quebec collapse came as cycle 22 climbed toward its own peak. But intense storm activity in that cycle continued well past it. The reason behind the pattern is reasonably well understood now. Near maximum, the Sun produces the largest raw number of sunspots, but the global magnetic field is in the middle of reversing polarity. The whole configuration is chaotic and disorganized during that reversal. In the declining phase, the number of regions falls noticeably, but the ones that do emerge tend to be larger and more complex. They also tend to survive far longer, across multiple rotations. At the same time, large coronal holes open across the surface. Those produce fast solar wind streams arriving on a regular schedule. That keeps the magnetosphere in a repeatedly disturbed and agitated state. There is a second reason the declining phase behaves this way. Coronal holes are regions where the magnetic field opens into space. Instead of looping back down, the field lines run outward. Solar wind escapes through those openings at much higher speed. During the rising phase, coronal holes are mostly confined near the poles. Their fast wind streams miss Earth entirely most of the time. As the cycle declines, those holes migrate toward lower latitudes. They begin appearing at latitudes that point their streams directly at us, and because the Sun rotates roughly every 27 days, they return. The same hole can strike Earth repeatedly across many months. Forecasters call the resulting pattern recurrent geomagnetic activity, and it repeats. That is the mechanism behind the disturbance that was running last week. That disturbance was not a coronal mass ejection at all. It was a coronal hole stream arriving exactly on schedule. A cloud arriving at a calm magnetosphere is one thing entirely. A cloud arriving at one already agitated for 2 days is another, which, as it happens, is exactly the configuration in place last week. A large coronal hole crossed the disk center around the 20th of July. It sent a fast solar wind stream directly toward Earth. That combined with a co-rotating interaction region behind it. That region is the compressed boundary where fast wind meets slower wind ahead. Hold that timing in mind, because it overlapped exactly with the flaring. Together they drove minor storm conditions from the 22nd through the 24th. The planetary index ran between 2 and 4 across that window, and the interplanetary field underwent several extended southward deflections during it. So the background was already disturbed when the region was firing. The magnetosphere was already being worked on continuously from another direction, and sitting at the center of the Earth facing disk was our delta region. That is the convergence, and it is not a coincidence at all. It is a structural feature of the phase we have entered. Mark Misch is a scientist at the Space Weather Prediction Center. He described the situation in an update this past May. He called the current period hurricane season for space weather, and he noted that some of the largest storms in history occurred during decline. Hurricane season is exactly the right analogy for one specific reason. It does not mean that a hurricane is coming tomorrow. It means the conditions that produce hurricanes are now fully present. It means the frequency of formation has gone up measurably. And it means that state will persist for a defined period. The declining phase of cycle 25 runs through the rest of this decade. This year and next sit in the middle of the dangerous window. I want to be careful about one implication of all this. None of it means that a severe storm is actually due. The declining phase raises the rate of formation, and nothing more. A raised rate across several years is still a low rate. Most declining phases pass without producing anything historically notable at all. What it does mean is that the base rate has moved. It moved upward quietly, without any announcement or headline anywhere, and it will move back down again over the coming years. The only real question is what happens inside that open window. Cycle 23 declined through the early 2000s without incident for years. Then, in a single fortnight, it produced the Halloween sequence. That is what a raised base rate actually looks like in practice. Long stretches of nothing, and then 2 weeks that enter the textbooks. And before I leave the Sun behind, I have to widen the frame. Everything I have shown you covers about 167 years. There is a far longer record that almost nobody has encountered. That longer record is not written in any instrument reading at all. It is written instead in tree rings and in polar ice. Part 15. The spike in a Japanese cedar nobody can explain. In 2012, a researcher named Fusa Miyake published a finding in Nature. She works at Nagoya University, and she was not studying the sun. She had been analysing carbon-14 concentrations in the rings of Japanese cedar. Carbon-14 forms in the upper atmosphere when cosmic radiation strikes nitrogen. Trees absorb carbon dioxide, so every ring records the atmosphere of 1 year. A sudden increase in carbon-14 means a sudden increase in radiation. Miyake found a sharp spike in the rings for a specific pair of years. Those years were 774 and 775. The spike measured around 12% above the surrounding background. For scale, consider what the Carrington Event left in the same record. It produced a carbon-14 signature of less than 1%. She found a second event and published it in Nature Communications the following year. That one corresponds to the years 993 and 994. Since then, several others have been confirmed by other groups. There is one around 660 before the Common Era. There is another roughly 14,300 years ago. And there is a candidate around 12,350 before the Common Era. That last one may be larger than any of the others. These are now called Miyake events, and the confirmations are unusually robust. The same spikes appear independently in beryllium-10 concentrations in ice cores. They appear again in chlorine-36 in the same cores. Those cores come from both the Arctic and the Antarctic. Different isotopes, different archives, different hemispheres, and the same exact years. Let that agreement register, because independent records rarely line up that well. The event of 774 is estimated at 10 times Carrington. That is the minimum estimate, and some analyses put it higher. I want to be careful about what that does and does not tell us. The physical mechanism behind Miyake events is still genuinely debated. Some researchers argue they may involve processes unlike ordinary solar particle events. The dating is extremely precise, but the energetics are inferred rather than measured. But the tree rings are entirely unambiguous about one single thing. Whatever the maximum output is for this star, it is far above our records. Our complete data set of directly measured solar events covers 1.5 centuries, and that dataset happens to contain the smallest events in the distribution. The upper tail of that distribution is written into wood and ice. We have been calibrating our expectations against the quiet part of the record. Here is another way to feel the same problem from a different corner of space. On the 15th of February 2013, an object entered the atmosphere over Russia. It exploded above Chelyabinsk with the energy of roughly 30 Hiroshima bombs. The airburst shattered windows across 6 cities in the region. Roughly 1,500 people were injured, almost all by flying glass. The object was about 20 meters across, which is genuinely small, and nobody on Earth saw it coming because nobody was looking there. That event is not a solar storm, and the physics is completely different. I raise it here because the underlying epistemic situation is identical. A category of event that had not happened in the instrumental era, so the planning assumptions were built on the absence of examples. Then one arrived, and the assumptions turned out to be about our records. Those assumptions were never actually about the world itself at all. That is the position we are in with extreme space weather right now. The 1859 event is not the ceiling of what is possible. It is simply the largest thing that happened while somebody was watching. There is a name for the error this creates in risk assessment. It is sometimes called the problem of the short record. Every estimate of how often extreme events occur rests on observations. If your observations span 1.5 centuries, that is your window. Events with a return period of 1,000 years may never appear. Their absence from your record is not evidence of their absence. the tree rings extend the window from centuries to roughly 10,000 years. And the moment that window widened, larger events appeared inside it. That is exactly what you would expect if the distribution has a tail. It is also exactly what you would not want to find. Hold that distinction, because it changes how you read every probability tonight. Now let me bring this back to the present and be specific. Active region 4493 sits in the western half of the disk. It is moving toward the edge at roughly 13 degrees per day. It should rotate out of view around the 28th or 29th. From that point there are two branches, and the data favours neither strongly. The first branch is that it simply decays on the far side. That is what the majority of regions do after their emergence stops. It is also what every other dominant region of this year did. If it follows that pattern, it will not return in recognisable form. By late August there would be nothing there to look at. The second branch is that it holds together and survives the trip. Regions reaching the size and complexity it reached sometimes do exactly that. Region 3664 survived 3 full rotations in 2024. It came back larger and more productive after each one. If 4493 survives, it reappears over the eastern edge. That would happen somewhere in the second half of August. And the first question anyone will ask concerns its magnetic complexity. Has the delta structure survived the crossing, or has it collapsed? I do not know which of those two happens next. Nobody does, and the verification study explains exactly why not. I would be suspicious of anybody claiming otherwise this week. What I can give you is a set of indicators rather than a prediction. If the region returns in August still carrying delta configurations, that is meaningful. It will have survived a full rotation with its complexity intact. That is precisely the behaviour that separated 3664 from everything ordinary. If the Space Weather Prediction Centre issues a G4 or G5 watch, that matters. That is the threshold at which grid operators begin taking protective action. It is the point where this stops being an abstract discussion entirely. If Starlink satellites deorbit after a storm, that is a direct measurement. It measures upper atmospheric expansion better than any model does. And the constellation is now being moved to lower altitudes deliberately. That makes it a more sensitive indicator than it was in 2022. And if agriculture or aviation reports positioning failures, that is Gannon repeating. That is the mechanism costing real money while nobody loses power. Which brings me to what we can and cannot currently see coming. Part 16. The 90% that teaches everyone to stop looking. Our ability to watch the sun is improving in one specific way. It is not improving in another, and the gap between them matters enormously. Here is the improvement first, and it is a genuine one. On the 24th of September 2025, a mission launched to the first Lagrange point. It flew aboard a Falcon 9 and reached its station upstream. That new spacecraft carries an instrument called the compact coronagraph. That instrument images the region of space immediately around the Sun. That is where coronal mass ejections first become visible after launch. It gives forecasters earlier and more reliable detection of an eruption. That improvement runs on the order of 1 to 2 days ahead. That is real progress on the question of whether something is coming. And here is the gap that still remains wide open today. It does nothing at all for the question that decides everything. Detecting an ejection leaving the Sun tells you it exists. It gives you a rough speed and a rough direction of travel. It does not tell you the magnetic field orientation inside it. That still cannot be measured until the cloud is almost here. The dates in this next section are the ones that matter most. There is a mission designed specifically to help with this problem. The European Space Agency has given that mission the name Vigil. It will be stationed not upstream of Earth, but behind us. It sits at the 5th Lagrange point, roughly 60 degrees behind in our orbit. From there it sees the Sun and the intervening space from the side. Giuseppe Mandorlo is the Vigil project manager at the European Space Agency. He put the difference about as plainly as anyone could. From the first Lagrange point, you see the ejection coming head-on. It is hard to judge how fast it is, or where it is going. From the fifth point, he says, you see the whole thing sideways. Matthew West is the mission scientist for the same program. He describes the goal as stitching together one continuous scene. That scene runs from activity on the Sun through the space between. It continues all the way to Earth's own space environment. Side-on viewing would give something like 4 to 5 days of useful notice. It would allow direct measurement of speed and structure rather than inference. Vigil is planned to launch in 2031 aboard an Ariane 6. That launch is followed by a cruise of roughly 3 years to station. Consider those dates against the phase we are currently in. The declining phase of Cycle 25 will be over by then. The capability that would let forecasters see one of these properly arrives late. It arrives after the window it would have been most useful in has closed. Meanwhile, the existing workhorse instruments are aging steadily in orbit. The Solar and Heliospheric Observatory launched in 1995. It has provided the coronagraph imagery underlying most ejection detection since. It was designed and funded for a 2-year mission. It is currently operating in its 31st year of service. So the honest summary of our forecasting position is uncomfortable. We can see the Sun better than at any point in history. We can detect an eruption within hours of it occurring. And we still cannot tell you, until the final hour, what it carries. Now I want to return to the number I asked you to hold. It is the last time it appears, and it has changed meaning. 10% of delta regions produce an X-class flare, which means that 90% of them never do anything at all. Think about what that ratio does to a person over time. Think about what it does to an institution over decades. Every delta region that emerges generates a small amount of attention. There is a forecast update and a slightly elevated probability. Perhaps a note gets passed along to grid operators somewhere. And then, 9 times out of 10, nothing whatsoever happens. The region rotates off the disk and the file quietly closes. 9 times out of 10, the people who paid attention were wrong. Wrong in the only sense that anybody ever measures afterward. Repeat that cycle enough times and you get a specific human outcome. It is well documented in every field that manages rare risks. The signal stops being treated as a signal at all. That does not happen through any decision anybody makes deliberately. Nobody stands up and announces they will start ignoring space weather forecasts. It happens through attrition instead, and through accumulated ordinary Tuesdays. So here is what I actually think the danger is. It is not the flare, which produced 5 brief radio blackouts. It is not the radiation storm, which never even occurred last week. And it is not exactly the coronal mass ejection either. Most of those miss us, or arrive with the wrong orientation. The system protecting us from all of this is not made of instruments. It is not made of spacecraft, or models, or standards documents. It is made of attention, and specifically of sustained attention. A relatively small number of people taking a rare event seriously. Doing that year after year, through long stretches, producing no visible benefit, and occasionally producing a very visible cost instead of a benefit. Attention is the one component that degrades from disuse rather than use. A transformer that is never stressed will last considerably longer. A satellite that is never struck lasts longer as well, but a monitoring program that never catches anything gets its budget questioned. A forecaster who calls elevated risk 11 times without an event gets ignored. On the 12th call, the operations desk does not pick up. That is the mechanism, and it looks nothing like a solar flare. It looks like a line item in a budget review. It looks like a reasonable person making a reasonable argument, arguing that the observed frequency does not justify the current expenditure. That person is entirely right about the observed frequency of events, and being catastrophically wrong about the shape of the distribution. Let me put the layers together, because the structure is what matters. The first layer is the physical event, and it is genuinely rare. Riley's estimate runs between 3 and 12% per decade. Even at the high end, almost every year contains nothing. The second layer is our exposure, and it has grown enormously. In 1859, the exposed surface was a telegraph network. Today it is 14,500 satellites and a positioning system. Agriculture, aviation and finance are all built on top of that. Add the undersea cables carrying almost all intercontinental data traffic. Add continental power grids whose critical parts take 3 years to build. The third layer is our recovery capacity, and it has moved backward. Not through neglect, but through the ordinary logic of efficient manufacturing. Transformers are built where they are cheapest, in the quantities demanded. That quantity covers normal replacement and not simultaneous regional loss. And the fourth layer is attention, which is the only one we control. It is also the one that erodes on its own when nothing happens. Hold all 4 of those layers together now, because they interlock. Those 4 layers explain the Gannon storm almost exactly as it happened. Layers 1 and 2 interacted and cost $500 million. Layers 3 and 4 were never tested at all that week, and they explain why the 2012 event is the most important entry. Layer 1 delivered a Carrington-class event to our orbital path. The other 3 layers went untested purely because of where we stood. Which brings me back to the question I opened with tonight. Part 17. What is still moving toward us? On the 18th of July, that patch of the sun was completely empty. By the 21st, it was 100,000 kilometres across. It carried 30 spots and multiple delta configurations at maximum complexity, and it sat at North 5, West 5, which is aimed at us. By the 23rd, it was producing nothing larger than C-class flares. 4 days, from emergence to irrelevance, and then it was gone. What strikes me is that the whole episode was legible to almost nobody. It was visible only to people who were already looking at it. There was no moment where the region announced itself to anyone. The 5 radio blackouts each lasted tens of minutes at most. They affected a band of the spectrum most people never knowingly use. Nobody's lights flickered anywhere on the planet during those 4 days. Nobody's phone stopped working for a single second because of it. And no newspaper anywhere in the world ran the story. If you were not watching the disc that week, the sun did nothing. So let me return to where this started, and to the question. Is a sunspot that goes silent the most dangerous kind there is? I cannot answer that cleanly, and I want to explain why not. A warning is defined entirely by whatever happens to follow it, and nothing at all followed this particular warning last week. If a large region emerges in August and produces something significant, this reads differently. Last week becomes a rehearsal, and everyone finds it obvious afterward. If cycle 25 declines quietly through the rest of the decade, it reads otherwise. Then last week was exactly what it appeared to be. 4 days of ordinary stellar weather that some people watched closely. Both of those futures are consistent with everything I have laid out. The physics does not distinguish between those 2 futures until afterward. What I can tell you is that both clocks are still running. The sun is 21 months into the phase that produces the worst storms. That phase still has several years left to run ahead of us. Underneath all of it, our exposure keeps growing every single month, and the recovery time keeps stretching further and further out. And the instrument that would let us see one properly arrives in the mid-2030s. They are moving toward each other, and they have been for decades. Last week they produced a region that made noise and then stopped. The noise stopping is the part I want you to remember, because the pattern in the historical record is not what people assume. These events almost never arrive without any warning at all. Carrington was watched live by 2 men through separate telescopes. Quebec was preceded by days of documented and logged activity. The Halloween storms came from a region visible for weeks beforehand. Gannon came from the largest sunspot group in 21 years. The warnings are almost always present in the record beforehand, and they are almost always indistinguishable from the identical warnings that meant nothing, which means the protection was never really the forecast itself. A forecast is a probability, and probabilities are wrong by design. The protection is whether anyone is still watching on the day it resolves. 4493 crosses the western edge within the next few days. If it survives the far side, it returns in the second half of August. If it comes back still carrying that complexity, I will tell you. I said at the beginning that the region emerged from an empty patch. That patch is empty again now, and it will not stay that way. Somewhere beneath the visible surface, the dynamo is still winding the field. It has been doing that continuously for 4.5 billion years. It will keep doing it long after every question tonight is settled. The pump is still running, and the balloon is still filling. Somewhere on that star, the next region is already forming underneath. Thank you for spending this time with me here tonight. Take care of yourselves, and I will see you tomorrow.